In our previous video, we have learned the relationship between Ka and Kb of their conjugates to be equal to 10 to the negative 14. This equation is particularly useful when we deal with amphoteric substances. We have learned in the past that phosphoric acid has up to 3 protons to release. So you can set up to 3 different equilibriums with 3 different constants. Okay. However, the same way that you have an acid and a conjugate base, this means that H2PO4, in other words, the dihydrogen phosphate, can behave both like an acid or like a base. The question is it an acid or is it a base? In this case, I'm just writing it like an acid, but notice that H2PO4 in water could also behave like a base, accepting a proton and forming this. Notice that if we call this Ka2, this would be Kb1, right? Because I'm dealing with the conjugates of the first dissociation here. Okay? So how do we know the value of Kb1? Kb1 will be 10 to the negative 14 divided by Ka1, or in other words, 10 to the negative 14 divided by 7.2 times 10 to the negative 3. This is going to be around 10 to the negative 10. We would need a calculator to know the exact number, but I apologize. No, maybe it's closer to 10 to the negative 11 probably. It's closer to 10 to the negative 2. So yeah. So what do we do with this information? This will allow us to know if the hydrogen phosphate is an acid or a base in water. How do we know that? Well, if we have written that this is 10 to the negative 8, so this is my Ka2 and this is my Kb1 that I just calculated up here. Oh, there you go. It's this value. Notice that this constant is larger. Therefore, when hydrogen phosphate or dihydrogen phosphate reacts with water, it will tend to go this way because this equilibrium constant is much larger. Four orders of magnitude much larger than behaving like a base. So it's not that this reaction will not happen, but this one up here will happen 4 orders of magnitude much more. Okay, so this is why we say that in this case the hydrogen phosphate is an acid.